One of the important pieces of technology that makes use of angular momentum is called a gyroscope. There are lots of ways to demonstrate how a gyroscope works, but the most common one is to take a bicycle wheel and get it to spin really fast. And here's a video of a very famous professor, Walter Levin at MIT, demonstrating what an odd thing a gyroscope really is.
Suppose I have here a string, a rope, like we have there. And I stick into that rope, I attach to the rope this wheel, just like so. And I let it go. Well, we all know what will happen. Plump. Clear. All right. Now I'm going to spin it before I let it go. Where's the wheel? The wheel is here. So we'll spin it up, and then we'll put it in. Notice the way I'm spinning it, holding it away from you now. I'm going to change it and do it differently next. There it goes. About 10 seconds. Isn't that amazing? And it rotates seen from below clockwise. Now it's going this way, and I'm going to redo the experiment, changing the direction of rotation, and then it will go the other way. Now the angular momentum, rotating like this, is pointing here. Spin angular momentum is pointing like this. Torque is like this. And so the spin angular momentum is chasing that torque. I'm the spin angular momentum, I'm the torque. This is the torque. It's chasing it. All right, so I have this in my right hand. It's all right. Now I will, so when I spin it up, we let it first go around, which was roughly 10 seconds, what we calculated. And now I'm going to put 2 kilograms here at the end. Now you'll see an instantaneous increase in the precession frequency. See, it goes much faster now. Take it off, and then it goes back to its roughly 10 seconds. So what I have done is, I have increased its torque.
Well, I'm sure you're like me. The first time you saw this, you're just thinking, why doesn't that bicycle wheel just fall straight down like it did before? All he did was spin it to go make it go faster, and all of a sudden it starts processing around like a clock on a hand, or a hand on a clock. It didn't fall straight down like it did when he first hung it on that rope. Well, this turns out to be a pretty amazing thing, and it's kind of critical to how a gyroscope works. We all know that gravity pulls straight down in this bicycle wheel, and it does so through the center of mass of the wheel, so acting where that green arrow is. But it's doing so at a distance r away from the pivot point, because he had it on an axis of some sort. So the place where the force pulling down is not equal to the place where it's going to pivot. As a result, this is going to result in a torque, an r cross f. And so the torque, if you use your right hand rule and start with your fingers pointing in the direction of r and curl them down in the direction of mg, your thumb will point into the page like that red arrow where I indicated what torque is. And so that's going to be a torque, not a straight force on this wheel. Now the wheel is spinning with an angular speed omega, and it has an angular momentum as a result that points out along the length of the axis of this bicycle wheel, away from the pivot point. So it has an angular momentum. If we were looking at this situation from above, the pivot point would be in the middle, and that angular momentum would point from the pivot point outward. And the torque causes a change in angular momentum. Remember that torque is equal to delta L over delta T, so a delta L is torque times delta T. That means at a later time, there's going to be a new angular momentum L final, and it's going to be over this way a little bit because I have to say L naught plus delta L equals L final. It's just vector addition. So that means the angular momentum vector is starting to sweep around in a circle. And in fact, it causes a change in angle, delta L over L, that we can actually calculate. When that delta phi, that change in angle, equals torques times delta T, or RmG times delta T, divided by L, which was I omega. And if we can divide both sides by delta T, that means there's a delta phi divided by delta T, a change in angle per unit time, equal to Rg times the diameter of the wheel squared times omega. Here I inserted what the moment of inertia I is for a hoop. It's just m times its diameter squared. And so that means this gyroscope starts to move around in a circle. It precesses, is what we call it, with an angular speed, delta phi over delta t, which is just related to how long of an axis it has, r. It's related to its diameter, and it's related to the amount by which we spun it. So gyroscopes try to keep precessing like this, and in fact, in that sense, they're useful for navigational tools because they always try to precess around the gravitational vector.